There's a lot of information in 3.5, which is why I split it up over 2 days. Not only is it 2 days worth of work, but it's 2 days worth of instruction. So today is what's called implicit differentiation. What I'm about to put up, you can write down if you want. You do not need to write this down, though, if you don't want to, okay? You can make that decision. All the differentiation that we've been doing so far has only contained one variable. Maybe you haven't noticed that, okay? Regardless of what the variable was. What we have been doing is called explicit differentiation. We never call it that, though. We just call it differentiating, okay? And so what happens when we have more than one variable? How do you differentiate? Well, we're going to learn about today. We can differentiate when there are 2 variables. We can differentiate when there's 3 variables, 4 variables, whatever. It's called implicit differentiation when we have multiple variables. All right. On the next slide, I'm going to give you sort of the steps that you're going to take to go through and do implicit differentiation. In many ways, it is very similar to what you've already been doing, with one sort of major exception. Okay? And then the final piece to it all is the algebra. Because again, as we've discussed many times, that's what kind of binds this all together. All right, so here are the steps. First step is we're going to do like we've done. Now, this is also dependent on the idea that there are only x's and y's in our expressions or our equations. If there were other variables, you just replace the x with something else, and we treat it the same way. So here's the first step. We differentiate both sides with respect to x. Okay. And this is the part about the y prime chain rule factor for any term involving y. So if we differentiate a term with y in it with respect to x, that's where we have to get into the implicit differentiation. Because if we differentiate an x term with respect to x, that's literally what we've been doing. More often than not, I know it's going to say y prime or dy dx. More often than not, you're going to want to write dy dx, not y prime. And the reason is you're going to have a bunch of y's already in your expression or your equation. And this is the best way to make sure we don't get them confused with each other. And in subsequent steps, you'll see it'll say either or. Honestly, this is preferred. And as we look at some examples, this will become more clear. But essentially what you're going to do is you're going to differentiate all the terms. The ones that already have just x's in them, you differentiate like normal. The ones that have just y's in them, you differentiate like normal, and you have to tack on dy dx because that's the chain rule piece. And then after you do that, you take all the dy dx's that are involved and you get them together. Get them together on one side, you get all the other terms on the other side. Because what we're going to do is solve for dy dx, since that's what we're trying to find anyway. And then from there you factor out the y prime or the dy dx and isolate it. And then we're done. Now, one of the things that some of you have asked as we've been working on some of these new rules, product rule, quotient rule, chain rule, that kind of thing. One thing you have to understand is you should, for every single differentiation you ever do, you need to consider the chain rule. I know I taught it as a separate kind of rule, but it's really embedded throughout every kind of expression or equation when you take the derivative of it. You have to consider that. That's why we come up with that little phrase, always be chaining. because it's literally always you should be looking for it. The only time you don't have to really worry about it is if it's just an x by itself. Okay? But as you guys know, it's very rare that it's just an x by itself. It usually has a bunch of other things. Okay? So we're going to go through several examples today. All right? And here is the first one. So in all these problems today, we're finding dy dx until we get to the very last example. Okay.
How many problems are there?
There are... I think there's about 4 or 5. So like I said at the beginning, the process of taking the derivative of each term is really the same as what we've done before. Okay, so when I take the derivative of x squared, that's what? 2x. Okay? When I take the derivative of 2y, here's where it changes, because it's not in terms of x. But the mechanics are basically the same. If you use the same power rule principle to take the derivative of y squared, what would it be? It would be 2y. However, because of the fact that we are differentiating with respect to x, this is why this is a place where we have to have the additional term. That's the chain rule, because what we've done is we've used the power rule and then we took the derivative of y with respect to x. And that's what this is, the derivative of y with respect to x. And then what's the derivative of 25? 0. So in terms of our first few steps, shouldn't be an issue. It's basically the same process. Okay, I had written it out before. Now the key thing is we have to isolate dy dx, because that's what we're trying to find. All right, so I have to get this by itself. And in this particular example, of course, we start off pretty easy. Okay, my first move is I got to move the 2x to the other side. Okay. And then I have to divide both sides by 2y. And then simplify. So dy dx is negative 2x over 2y, and the 2's cancel. Write that out. So there you go. Hopefully that wasn't too big of a deal. Yeah? Well, this is first one. So the terms are fairly simple. What gets interesting is when we have multiple variables mixed in together and not separate like they are here. Okay, these are separate. We don't have them mixed in. But in this example, now they're mixed in. Okay, meaning, so like here I have x's and y's in one term. Let's do one piece at a time here. Okay, so let's start with this first one. This one's pretty straightforward, right? Derivative of x squared. What is it? 2x. Okay. Now what am I going to have to do with this? This is the product rule. Okay. Now, here's the way that I would think about this, just to make things easier. Think of the first function as 2x squared. Just keep the 2 with the x squared. Just easier that way. And then keep the y sort of separate. Okay. So, 2x squared times the derivative of y plus y. What's the derivative of 2x squared? 4x. Okay. Derivative of 1, 0. Don't even need to write anything. You could write 0 if you wanted. What am I going to have to do with this? Product rule again. Okay. So this is plus x times 2y dy dx plus y squared. What's the derivative of x? 1 plus 3y squared dy dx. So here's where it starts getting a little more involved, right? Because I have 1, 2, 3 dy dx's. And I have to gather those all together on one side and move everything else to the other side. So here's what I had when I wrote it out ahead of time. Okay, I did not put the 0 for the derivative of 1. Now, it would be helpful, again, to get all the dy dx terms on one side and all the non-dy dx terms on another side. I think I probably cleaned this up a little bit first. Oh, not yet. Okay, good. So I need to get those three things together on one side so that once I have them all together on one side, I can just factor the dy dx out. And then I need to have all the unhighlighted terms on the opposite side. So this is where, from this point forward, it's all just algebra. We did the calculus. Now we've got to do the algebra. Okay, so here's what I did. I just slid this term here to this side. So now I rearranged this a little bit, right? X times 2y is 2xy. This stays the same. This goes at the end. That's where I put it. You don't have to necessarily put them in this order. And then I move the y squared term to the other side. And again, I multiplied this out a little bit, 4xy. So my 2x, 4xy, bring the y squared over. Okay, questions so far? We're following along, okay, we're good? Yes. All right, so now I gotta factor out the dy dx. And then divide, and we're done. I mean, we want to reduce if we can. So I just divide both sides by that. And there is that monstrosity. This on top, this on the bottom. Now, you might, like, this is not factorable up here. You got a y squared and x. You know, it'd be nice if there's, whenever you have an xy term, it'd be nice to have an x squared and a y squared. But I don't have that here. Even though I have that down here, since this is not factorable, there's no reason to try to factor this, which it's not factorable either, by the way. And that's really as far as we can go with that. Another way that we could think of these problems, and I'll write this in at the top, is that we're taking, it's like d dx of the whole thing. We're differentiating with respect to x. And so since there's a y, when we take the derivative with respect to y, that's where this y pops in. So yeah, it basically is, if you're differentiating with respect to whatever the variable is, and this variable in the problem is different from this, that's where you have to have that extra add-on piece, okay? Yes, you could use y prime instead of dy dx, but I caution you to do that, especially in a situation like this, right? Like if it's sitting right here next to a y term or another y term, if you leave a prime off or you treat it like a power, that's where you could have an issue, and I don't want that to happen to you, okay? All right, let's look at another one. Next one. So those first couple involved pretty much power rule, product rule. We didn't have to, I mean, the dy dx's are changed. you also are taking the derivative of x with respect to of y with respect to x. There it is, and that's where that chain rule piece comes in. Now here, okay, derivative of 1, of course, is 0. Derivative of x is 1. Now when I take the sine of y squared, now, is this sine squared or is this y squared? It's y squared, okay? If we wanted it to be sine squared, the 2 would be in between the sine and the y. All right? So when I take the derivative of this side is 1, okay? What is the derivative of the sine? Cosine. So I got cosine y squared. Is that it? No. Okay. But then I have to take the derivative of y squared. Okay. And that is 2y dy dx. Because we are taking the derivative with respect to x. Okay. Go ahead and simplify that. Get the dy dx by itself. All right, now, I start off here. Okay, so 1 over this. I put the 2y in front. Is this good enough? We're done? No. Could we do more? Right, 1 over the cosine is the secant. Okay, so when we can do this, it's probably better to do that. But understand, this goes back to what we were talking about before. You have a multiple choice question. This happened to you on your test. A lot of you are like, oh, natural log of 3 is not on here, Mr. Zukin. Well, that's the same thing as natural log 27. Okay, and so, yeah, it was. Same idea. You'd have to look for one of these. One of these is going to appear in a multiple choice question. So you just have to know how to do that. And also, the sine squared plus the cosine squared is always what? 1. You shouldn't have to be told to look for that. If ever you see that, change it to 1. That was also on your test. Okay, next. Okay, find the equation of the tangent line of the curve. So now we have an application. So go ahead and give this a shot. Go ahead and see if you can, because the slope, we need the slope, right? If we're going to write an equation, just like in algebra, well, the slope is dy dx. The only difference between what we've been doing and what we're doing now is we're going to get an actual value for that slope. So previously, when we would evaluate the slope and find out what it was, or the first derivative, its value at a certain point, we only had an x. But now we're going to have an x and a y. So instead of evaluating just at a specific x value, you have to evaluate at the x and the y value at the same time. And that'll give you the slope for the tangent line. All right, so I'm not going to show you the whole thing, but let's just see where we're at with the derivative itself. Okay? Again, you've got product rule here. Don't forget this product rule. Okay, so if you didn't do the product rule, it's going to be wrong. So let's go back to fix that, right? This is 2x times y. So again, I just think of the 2x as one function and the y as another one. Okay. So based off of some of the sounds I was hearing, we'll just kind of wait for a second because we got to clean it up. Again, we got to gather the dy dx terms on one side, the other terms on the other. So this 1 goes over, becomes minus. This 2y goes over, becomes minus. This 2x goes over and becomes minus.
Why did the y be positive? The plus y times 2, why did it become positive? Oh, wait, never mind the product. Never mind.
Yeah, over here. That's from this one. Yeah, you're looking at this one, which is still negative. That's all right.
Could you put the dy dx on the right side?
Sure. Yeah, no, it doesn't matter. You just got to get them on opposite sides. Okay? And so then I factor out the dy dx. So right, so probably what you have, if you put the dy dx on the other side, is these were all positive and these were flipped around. So if you had 1 plus 2x plus 2y, and then you had 2y minus 2x on the bottom, instead of the way I have it, it's the same thing. It'll have the same value. It's just, it's off by a factor of -1, right? On the top and the bottom, which means it's not off at all. Now, we were asking about notation because we have to evaluate dy dx at the point 1, 2. So here's what that notation would look like. Okay, so we still have the vertical bar, and now we just put the whole point. Instead of saying x equals 1 like we were doing before, you don't have to say x equals 1, y equals 1. Just put the point there. And this sort of subscript below the bar tells us what we're evaluating at. Okay, and again, if you had the top is all addition and this two flipped around, you know, this is going to be a little different, but your slope's still going to be the same. So I plug the 1 in everywhere there's an x, and I plug the 2 in everywhere there's a y. So -1 minus 2, that's -3. Minus 4 is -7. And this is 2 minus 4. That's -2, so 7/2. Okay? And from there, we're basically done. Point slope form. Plug it in. Y minus 2. 7/2 is x minus 1. One more example. And it's a little bit of a doozy. Okay? We can take the second derivative using implicit differentiation. Okay? In the notation, I've showed you the notation before, but we really haven't used it. The second derivative notation looks like this. Okay? This means second derivative. So the 2 will always be, on top will be over the d, and on the bottom will be over the x. All this means is the second derivative with respect to x. Here's the thing that's really important to understand, bless you, that whenever we have a problem like this and we have to use implicit differentiation, there should be a place where we will be able to reproduce this part of it and replace it with the constant that it equals. Okay, let me say that again. At some point, towards the end of this problem, you should be able to find a square root of x plus the square root of y. And if it's not there, you should be able to factor in such a way that it appears. Because then you are going to replace this with this 1. Okay? That's really important on these kinds of problems. Is that in the end, you're going to be able to simplify even further based off of the problem that you are given. Okay, that's important to understand. All right, so go ahead and take the first derivative. Let's start there. Take the first derivative. All right, what's my first move going to be? Here. Yeah. So make this x to the 1/2 plus y to the 1/2 equals 1. Okay, go ahead and do first derivative, please. The first derivative means we are finding dy dx. Okay, you can't just do half of it and be done. You have to get dy dx by itself. So here's where we should have started. Okay, 1/2 x to the -1/2 plus 1/2 y to the -1/2 dy dx. The derivative of 1 is 0. Okay, I gotta move some things around and divide to get dy dx. Now, there's a reason that I left it like this. Okay, you don't have to leave it like this. You could switch these and put this to the bottom, move this to the top. I didn't do that. And let me explain why. Some of you have figured this out, some of you have not. It is possible to avoid the quotient rule. Okay? By not moving this term down, this problem is a product rule instead of the quotient rule. That is legal. That is allowed. Okay? And I'm just telling you my own personal preference. If I don't ever have to deal with the quotient rule, I'm not going to. I'm going to use just the product rule if I can. Okay? So here's the thing that you have to understand. We have only found the first derivative. In order to find the second derivative, we have to take the derivative of the first derivative. So now I have to differentiate this, okay, in order to come up with the second derivative. Whether you have it in this form or you have it as y to the 1/2 over x to the 1/2 is up to you. If you put it as x to the 1/2 on the bottom, that's fine. You're going to have to use the quotient rule. And that's okay. You can do that. I didn't do that, however. I'm going to leave it like this. So, product rule says, and again, I'm going to keep that negative with this. I'm treating this like, rather than sort of removing the negative, I'm just going to keep it with the x to the negative 1/2. Okay, so I'm going to multiply that times the derivative of y to the 1/2. And then I have my chain rule piece. And then I'm going to take this, this times the derivative of this. Okay?
Put it back to be equal to 0.
No. Nope. We're just straight up taking the derivative of this with respect to x. So again, I use product rule here. First function times the derivative of the second. Since it's a y, I have my dy dx. Then my second function times the derivative of this. Now notice something here. When the negative 1/2 comes down, it gets multiplied by this negative. That's why this 1/2 is positive. Subtract 1 from this, I get negative 3/2.
How is it the chain rule though? Isn't this just
The chain rule, because we're differentiating with respect to x, and when I have a y term, I have to also take that derivative of y. Now, here's the problem, or what you would perceive as a problem at this point is, I have this dy dx. What am I supposed to do with that? How am I supposed to deal with that? Right? Let me simplify this a little bit first, and then I'll show you how we deal with that. Okay? So all I did here is I just simplified this front part, moved the half to the front, because that's where coefficients go. All right? And then here I put it in descending order. Put the x first, then the y. Here's the problem that we have with this dy dx. It's still there. And I can't have the second derivative while the first derivative is still there. So what we do is we know what dy dx is. So that's got to go in there. We replace it. And that's why finding dy dx first is really important, because that's going to go right in there. Okay. And now I can multiply this out, simplify, and then I got to look for this still. So remember, when we multiply exponents with the same base, we just add the powers. So this negative times the negative is going to turn positive. X to the negative 1/2 times x to the negative 1/2 is x to the negative 1. The nice thing about the y's, they go away. Y to the negative 1/2 times y to the 1/2 is y to the 0, which is just 1. This is just along for the ride at this point. We're not doing anything with it. Okay? So that's what I'm talking about, where that y went away. Now here's where our factoring is going to come into play. I think I moved to the next slide because I'm running out of room. Nope, I got one more move here. One more move before we move to the next slide. Okay? What is the smallest power between the x's? Negative 1 or negative 3/2? Negative 3/2 is smaller than negative 1. So I'm going to factor x to the negative 3/2 out. And the 1/2. I can factor the 1/2 out. So when I factor it out, it's negative 1 minus negative 3/2, which is 1/2. Negative 1 minus negative, because it's division. x to the negative 1 divided by x to the negative 3 halves. That's negative 1 minus negative 3 halves, which is positive 1 half. Bing, bing, bing. What do we got here? This is where we started. Okay? So now I'm going to move to the next slide. I'm just going to repeat this real quick. Back to this. I told you it was a doozy. Just factoring. I'm going to go to that one too, yes. Okay? So again, I think what trips some of you up is this factoring. Okay? Remember that negative 3 halves is smaller. Whenever we factor with variables, you take the smallest power out. And then it's division. Right? X to the negative 1 half divided by x to the negative 3 halves. I'll write this out so you can see what I'm talking about. X to the negative 3 halves divided by x to the negative 1. Okay. Negative 3 halves minus negative 1. Or sorry, I did it backwards. My bad. My bad. Negative 1, negative 3 halves. So that's why it's x to the negative 1 minus negative 3 halves. That's where this term comes from. Okay. All right. Then the last slide to where we get to our final answer. Okay. Okay. Just going to repeat that. I just repeated that because I'm running out of room. Okay. So this is this, which is, what the freak? There it is. And so the second derivative is just 1 half x to the negative 3 halves. You can move it down and simplify it and all that stuff. But that's where all that algebra comes in. Okay? Do you need me to go back? Okay. Okay. So yeah, I think I gave you one of these. And it took me 2 slides. It's going to take you a few lines. You have an unlimited supply of paper. It's fine. Okay?